Okay, today we're going to be talking about gas pressure, and we should probably define what gas pressure is. So here's our definition. It is a force that is exerted by a gas on an object. Now, we know that gases are all around us. We have gases such as air that we breathe, and air is made up of a few different gases. We've got some nitrogen in there, we've got some oxygen, a little bit of carbon dioxide, and some other gases as well that make up air. And these molecules are always moving, and they're moving very rapidly, and they're always colliding with us and objects such as a balloon or anything that they can collide with creates pressure. And this is due to the collision of gas molecules with the surface, and that surface could be us, it could be our eardrums, and we might feel it. As we go up in an airplane or drive up in the mountains, we might feel it. When we dive underwater and swim down to the bottom of a swimming pool, we feel that pressure on, or release of pressure on our eardrums. Now, a model of what this looks like is given here in this container, and each of these pink boxes here represents a gas molecule. And we know that gases are moving, they have a lot of kinetic energy, and they are always bouncing off of themselves, and we're bouncing off the surface of the container. And so them bouncing off the surface of the container creates pressure inside this box. And one of the things that we'll learn is this pressure is related to temperature. So if we increase the temperature in this container, what we're going to do is we're going to increase the pressure. And the reason why we'll increase the pressure is these molecules will then have more kinetic energy. They will be moving faster. And if we lower the temperature, what's going to happen is we can lower the pressure. And this is one of the main reasons why there's warnings on the side of aerosol cans that tell us don't put it in the fire, because it'll increase the pressure of the gas molecules inside there so much it could explode. Now, we do need to mention that there is an idea called a vacuum, and this is a place where there's no pressure. Now, no pressure can be for two different reasons. One is you don't have any gas molecules. If we can remove all the gas molecules from inside a vessel, we won't have any pressure in there, and we'll call that a vacuum. We could also cool. We can cool the gas molecules to where they don't have any kinetic energy, and that is very difficult to do, and it would be 0 Kelvin. That would be our absolute zero. And so at absolute zero, if the molecules aren't moving, they cannot collide, and if there's no collisions, there's going to be no pressure. Now, we can measure gas pressure most typically with a barometer. And that's a definition that you definitely need to know. And here's a couple different types of barometers that measure atmospheric pressure, the pressure of air molecules bouncing off of us and bouncing off of everything else. Well, we can have an aneroid barometer, which is typically the type of barometer most people are familiar with. And this is one right here. And it does measure pressure. This one measures pressure. As you can look in there real closely, you see 760. We'll talk about that number here very soon. Now, you see that it's written on here that it says stormy here, rain, and then maybe very dry here. As storm systems move in, the aneroid barometer usually reads a lower pressure system, and sometimes you hear weather people talk about this. Or high pressure systems sitting over, like California right now, there's a high pressure sitting over us, so we don't get very many storms. It's very, very nice weather, although we need some rain. There's also a type of barometer called a mercury barometer, and so what a mercury barometer is, and this is some mercury here. Their mercury symbol Hg, and we have a glass dish or metal dish filled with mercury. That's represented down here. This is all mercury, and then we have this this tube which is open at one end and closed at the other end. You notice at the top it's closed, at the bottom it's open. We fill it up with mercury. We invert it into the mercury that's already in the dish at the bottom, and what will happen is the level of mercury will drop, and up here, above here, we have a vacuum, and as the atmospheric pressure pushes down on the mercury, it causes this column of mercury to rise and to fall depending on how much atmospheric pressure. So this would be an idea of a mercury barometer. Now, there are some units of pressure that we need to recognize. And so down here at the bottom, we have some units of pressure. And so we have three typical units used in our introductory chemistry class. The kilopascals, kPa is the abbreviation for that. Atmospheres, which is ATM, and millimeters of mercury, which references that mercury barometer we just talked about, which is mmHg. Now, if you were to go down to the gas station and want to pump up your tire on your car or truck or something like that, you wouldn't measure in any of these pressures. You would most likely measure in another unit, which is called PSI, which is pounds per square inch. But we can easily transfer or translate pounds per square inch into kilopascals or atmospheres or millimeters of mercury. And even some car tires do list atmospheres or kilopascals on the side of the tire, telling you how much pressure you should inflate a tire to. But the most common measurement in the United States is PSI. Chemistry, we use kPa, ATM, and millimeters of mercury. And so let's talk about, real quickly here, our standard pressures. Now, hopefully you remember when we talked about STP before, we said standard temperature and pressure. We said that the standard temperature was 0 degrees Celsius, which we could easily convert to Kelvin by added 273. Well, the standard pressure will be given to us on the back of our periodic table is 101.3 kPa, which is equal to 1 atmosphere, which is equal to 760 millimeters of mercury. Those three measurements are equal to each other. So we can use those to interconvert, and occasionally we do have to interconvert pressure measurements to make them cancel out in a problem. And so I'm going to show you how to do that right now. Okay, so this very first problem here, we have an example. It says convert 50 kPa to millimeters of mercury. So we're going to set this up with, once again, there's our known quantity. And we're converting to millimeters of mercury. There's our unknown. And so we're going to set this up in a one-step problem just like this. And we're going to put our known here, 50 kPa. And we're going to put our unknown here, millimeters of mercury, just like that. It should look familiar from a mole conversion or stoichiometry conversion. Then what we're going to do is we're going to take the unit that's listed right here that I'm underlining in red, and I'm going to rewrite that unit on the bottom, kPa, just like that. Now, the last thing I want to do is I'm going to plug in numbers from my equality, and here is my equality right here. And so, in front of millimeters of mercury, I have 760, which is given right there, so I'm going to write 760 right there. And in front of kPa, which is on the bottom, there's kPa on the bottom, I'm going to plug in 101.3 because that's the number that is associated with a conversion. So this problem becomes we're going to multiply 50 times 760, and then we're going to hit equal on our calculator, and then we're going to divide by 101.3. So let's punch that through our calculator real quick here. Okay, and so the answer that I get in my calculator is I get 375 and a lot of decimals. Now, I do have my known quantity with 2 sig figs there, so I'm going to go ahead and round this off. 375 is going to round off to 380. That would be just 2 sig figs, or we could even write it as 3.8 times 10 to the second. Those would both be acceptable. Now, we're going to cancel out units. We have kPa on the top, kPa on the bottom, so our answer is going to be in millimeters of mercury as a unit, and either one of those answers is acceptable, just like that. Let's look at this next one here. So, we have our known quantity as 2.5 atmospheres, and we're going to convert, in this case, to kPa. Now, I'm going to look at the equality, and from the equality, we have 1 atmosphere is equal to 101.3 kPa. And so I'm going to take my unit of ATM and I'm going to write it on the bottom just like that. And now I'm just going to plug in values for my equality. The number that goes with ATM is 1. The number that goes with kPa is 101.3. And so atmospheres is going to cancel. It's nice when there's a 1 on the bottom. I don't actually have to do anything. So 2.5 times 101.3. Round off to 2 sig figs. I'm going to call this 250 kPa, or we could also call it 2.5 times 10 to the second kPa. And that is how we can convert from kilopascals to atmosphere to millimeters of mercury.